This is just basically an introduction to HF propagation. The topic is massive. There's unbelievable amount of things that you can learn about this. This is just a shallow dive into it. So, what is propagation? It essentially is the movement of a wave through a medium. Why does this concern us? Because this is how RF communications between two locations occurs. We propagate through a medium. It's not the ether. Don't worry about that. We're not getting into that kind of goofy stuff. But essentially, RF waves travel in a straight line. So how does communication over the horizon work? That's what we're concerned with. How do I get that DX station? We have to use refraction. We're going to actually bend the signal, and we're not going to do it. We're going to use the ionosphere to do that. So what is refraction? It is basically the change in velocity when transitioning from one medium to another. So remember, you have your equation, C equals F lambda, where C is the speed of the RF wave, which is, it's an RF wave, so it's the speed of light in meters per second in a vacuum. That value, that 300,000 kilometers per second, is in a vacuum. Keep that in mind. Frequency is in hertz and wavelength is in meters, so then you have this balanced equation. So if we're changing something, we're going to change the speed of light. Essentially, we're going to slow it down going through this medium. Something has to change. The frequency is not going to change, so it's got to be the wavelength. So what about refraction makes the RF wave bend? When the RF wave meets the media transition boundary at an angle, different parts of the wave change speeds at different times, bending the wave. So I'm thankful to the ARRL. I grabbed a bunch of their stuff from the handbook and put it in here because they do much better with the art than I do. So as you can see, you've got a medium with a low refractive index. The direction of the wave is hitting that boundary, so that change. So think about it in your high school physics class. You have the prism, and you put the light through there. When the light hit it, that's one of the reasons why it's sloped, is you have a change in medium. It's going from the atmosphere into the crystal and then out the other side at an angle, and that's what it's doing. It's taking it and bending it. As you can see on the one side, you see those waves are a certain distance apart, and on the other side, they're another distance apart, but it's at a different rate. That's where you get your bend. So note that the refractive index is the ratio of the speed through the medium versus a speed through a vacuum. This is just some details. Keep it in mind. It's not going to be on the test. Also note that the amount of bending is the ratio of the refractive indices between the two media. So if you're coming in from nothing into the ionosphere, you have one thing. If you're going through different layers of the ionosphere, you're going to get different factors. So refraction and propagation. Line of sight, there's little refraction due to a constant refractive index in the atmosphere. So if I have one HF or one HT, you have another HT, we're not going to see much because we're in the same medium. As the altitude changes, the air pressure changes, which does change the refractive index. But again, the atmospheric changes here at the surface, pretty minimal. Even at an airplane, pretty minimal. Anything where you can fly something, pretty minimal. But the higher the ratio of refractive indices, the more reflective the transition. So this is where the ionosphere comes into play. That's a totally different medium. So you all know about the structure of the Earth's atmosphere. I kind of wanted to put it together one way, but I did it another way. So you got the diagram on the right, and then on the left, we got the list going from bottom to top. So your troposphere, which is where our weather is, stratosphere, which is way up there above where the airplanes fly. The ionosphere is where we begin to get the ionization of the top levels of the atmosphere, and then the magnetosphere. Just as a note, the ISS flies at about 450 kilometers, so it's in the upper F region. So it is in the ionosphere. So each layer has a different refractive index. This refractive index is not constant through the layer and changes as the density changes. Remember, we talked about the refractive index is based on density. So this creates the difference between a virtual and actual refractive height. The refraction is a gradual change. So you do have a virtual height versus an actual height. So as it's going up, as you notice in the diagram here, it's slowly starting to bend. So your calculations may not be correct. If you do have your actual angle of elevation, where you think it's going to come down at, it may not, because it's bending. It's not actually, it may not be reflecting. Density of the layers doesn't change much, but the density of the charged particles in the ionosphere does. So so the ionosphere has the same amount of material in it. It's just when you ionize it, you are starting to pull those pieces apart. You still have the same number of pieces, so the density is not changing. The density of its ionization, its charge is what's changing, and that's what's going to come into play. The primary reason why our atmosphere ionizes, UV radiation from the sun. We do get some X-rays and charged particles, which also ionize, and we'll learn about those in a little bit. But the magnetic field comes into play, and this is where it gets funky. It makes the ionosphere birefringent. So what does that word mean? It means that the ionosphere has two refractive indices, which means that if you put a signal into the ionosphere, you can have two different signals coming out of it. You have an ordinary ray, or O mode, and you have an extraordinary ray, or an X mode. They are circularly polarized in the opposite direction. So even if you're using a vertical or horizontally linear dipole, vertical, whatever you want to call it, it doesn't matter. It's going to come out circularly polarized. But that really doesn't impact your receiving end too much. But just know that really, when you're putting it up there, you're getting two rays out of there. It becomes more pronounced as you approach the magnetic poles. So as you approach the magnetic pole, you're going to see more and more of it. As you approach the magnetic equator, you'll see less and less of it. So people up in Alaska do see a lot more of this. It comes into play a lot more. This also means that the ionosphere is not reciprocal. So people always say, well, you know, if you can hear them, you can work them. Not necessarily. There are times when you may be hearing their X mode and there's no path back because you don't have an X mode to them because they're just going the other way and you don't have an O mode to them. So how do we measure the ionosphere? We have a device called an ionosound, which is basically a portmanteau of ionosphere and sound. Remember the sounding devices, I think we still use them back in the 40s and 50s where we'd launch rockets up and take measurements of the atmosphere. Well, this is an electronic version of that. It is essentially a vertical sweep radar. It goes and starts off at one frequency and takes about a minute to do, and it goes all the way through a range of frequencies, and it sends a signal straight up. And then you see there's two antennas. There's a transmission antenna and a receiving antenna, and we get that reception. And then on the right-hand side is the actual computer that interprets that. This is a map of the digisounds, which are basically ionosounds that are digital. They will convert into digital information. And this map, it's on the resources later on. If you want to, you can get it. You can click on any one of the green ones or the blue ones, and you can go to that actual, and I'll show you later. You can actually get and see their ionograms, because that's what an ionosound does, is it produces ionogram. So this is the reason I chose Boulder. I tried to use Wallops because it is on the East Coast. And if you want to do DX East, that's where you're going to be looking. So what happens is this thing is looking directly above it at the ionosphere. What's it doing right at that point in time, directly above it? So you usually want to try to find something between you and where you want to talk to. So like I said, Wallops is pretty good because it's on the coast and you're heading out towards, the east, heading out towards Europe. There's one at Lowell University in Massachusetts. That one has limited data. Wallops, I was doing all the stuff with Wallops, and then Wallops, some of the dates I was using had some problems. I couldn't get good data. So someone recommended Boulder, and part of the reason is I will have some clips from WWV, and that's near there. So if you're going to the West Coast, you might want to talk to those. I took a look at Alpena, which is the closest one to us in the Upper Peninsula of Michigan. Same thing, the data is a little not good for example purposes. So, but this guy here is a really good example. There's a lot of data on here, and there's a lot of data I don't completely understand, but there's a lot of data that I do understand, and it's actually pretty good. So this over here is the electron profile. This shows you the ionization of the atmosphere. Across your x-axis is your frequencies, and across your y-axis here is your height, how high up the signal is going. So what it does is it basically sends it up, and if it gets reflected back, you got a signal. This cloud up here is, remember, the Earth is also a reflector. So the signal went up, bounced off the Earth, and went back up and bounced off. Well, it didn't go that high. It's just that, remember, it's actually time of flight. That's how it does it. So it knows how fast the signal's going, and it knows when it comes back, that's how high it went. So that's basically false. That's not really there. The pink and the green are your O and X modes. So you see over here, you begin to see this divergence where the signal is acting differently. Over here, you see the F2. That's your F2 layer. I'll get into layers in a little bit here. This is the critical frequency. The critical frequency, I'll explain that in a little bit. But I'll do it now. The critical frequency is where it stops sending the signal back. So the reflection is no longer back directly down. So that's no, you don't. Hold on to that thought. It's not muff. The two are very related, but they're not the same. So the F2, so when we talk about the layers, the F2 layer is at 9925. The F1 layer is 497. So you can see, here's the F layer. Then over here, you can see a little bit of the F1 layer over here. Then over here, you're going to see, you got the E layer. This is right over here too. The D across the bottom here is the distance of your hop. So if you're having a 100-kilometer hop, your muff is the maximum usable frequency between 2 points. So as you get further and further out, I'll jump ahead and I'll show you. Your muff changes between 2 points. So if you're at M talking straight up and down, your muff is your critical frequency. But as you begin to aim your signal more and more horizontally, the ionosphere is going to refract it differently. So 10 megahertz will work to go from C to D. 14 megahertz will go from B to E. 28 megahertz will go from A to F. So that's what they're trying to show you here is if you're going to go 100 kilometers, you can use anything right around 10 megahertz. If you're going to go 200 kilometers, so at this point, it's nothing but trigonometry. I'm aiming my signal. Where do I want to go? So how high up do I have to go? And then pick your distance, and that's your maximum usable frequency. And there are tools that will help you do that. And let's see if there's anything else interesting on here. So you got your F2, your F1, F1 prediction. And the E layer, the prediction. And I think that's really about it for this guy. That's really pertinent for us. But you can see all along here, all of these frequencies are available. Any one of those will reflect back down. So yeah.
This with it.
Yep.
Yes.
I mean, I've never seen that done in the amateur.
They do it by stacking.
Yep.
Oh,
And phasing.
so they stack them at different.
Stack them at different heights, and then you can also phase them to get that. But I don't know if anybody's ever tried to mechanically rotate on each other. I don't think it would work.
One of the things you do is with the dipole, changing the height of the dipole, because that's where you're using the Earth as a reflector. So you just have to so what's going to boil down to, and I get down to the very end here, is it's not that it doesn't matter, but here's some key things you can look at. So don't really worry too much about that. But if you really want to try to communicate with somebody, you can start figuring out, you have the tools in place. So if you can figure out what your angle of what your launch angle is based on the height of your dipole, you begin to figure out where your signal's going. So where's my, okay. All right, I seem to be missing a couple slides here because I talk about muff, but here's the LUF. That's also the lowest usable frequency. Yeah, I know. I'm glad I did because I seem to be missing 2 slides. So yeah, we got the critical frequency, then you got the maximum usable frequency, you got the lowest usable frequency along a path between 2 points. This is determined by ion absorption. So remember, you're passing through basically the ionosphere is a plasma. You're sending a signal through the plasma. It's going to absorb some of that energy and also noise at the receiving end. So the interesting thing is that you can improve your LUF by increasing your transmission power, using directive antennas, and lower signal to noise ratio modes like CW, FT4, FT8, things of that nature. You can't use those techniques to improve maximum usable frequency. Maximal usable frequency, you just can't go past it.
I think I have a question here. Does mode come into play, AM versus a single sideband?
No.
The reason I asked that, I've been reading some books, and SAC in the 60s went to single sideband because LeMay and Collins proved that they could have worldwide contact with the B-52s. But they did it by going to single sideband, and I wondered if that had any power.
Yeah, the rule of thumb is that it's power. Yeah, it's how much how much you are generating RF. And with AM, with traditional AM, you have an upper sideband, a lower sideband, and a carrier wave. So you can have AM double sideband suppressed, so you can get rid of the carrier, but then you have to have a generator in an oscillator internal to the radio, or you can remove one of the sidebands, and by suppressing that, more of your energy goes into that sideband. Same thing with why is CW work even better than phone, because it's the same thing. You're compressing more and more of that signal into a type. So it has nothing to do with this. It's all about that is all about the energy on the wave. This is all making sure the wave gets to a certain location, and depending on how much the weight of that energy is being absorbed. So it doesn't matter if you are putting an AM wave into there and you're losing 50% or 50% of a CW wave. It's just how much of that energy is being absorbed. And with LUF, you can put more energy in there. So yeah, that's one of the reasons why CW is better for DX in the long run, because it's concentrating more of that energy into a smaller signal footprint. Let's see, where was I? So let's talk a little bit about the layers. So the D layer, this one only exists during the day. It absorbs most frequencies below 5 megahertz. The higher the signal frequency, the easier for it is to pass through. So stuff above the 5 megahertz. One of the reasons why it only exists during the day, it is ionized by solar hydrogen and short X-rays. And the particles it breaks apart combine very, very quickly. So as soon as the sun goes down, the D layer disappears very fast. 7 through 10 gets through, but as you lower your angle, you're spending more time inside of it, and it attenuates the signal more. The E layer, now I'm really not going to get into a lot of details because the E layer and this one is open for a lot of experimentation. The E layer is one of the more fascinating ones. It's like the D layer, exists primarily during the day. It takes shortwave UV and long wave X-rays, and it breaks apart nitric oxide and molecular oxygen and ionizes those. The daytime critical frequency is between 3 and 4 megahertz. Long distance, low angle, 5 to 20 megahertz if the signal doesn't get attenuated too much by the D layer. So remember, you're going through all these different layers, and each one of them has these characteristics you have to watch out for. The thing is, there's lots of different types of E layer propagation. You have sporadic E, you have auroral E, you have meteor scatter. So E is open to a lot of different things that you can do with it, but it's also can be a pain to work with because it's not as well known. But the F layer, that's the one. That is the one that is most important for long distance HF communications. This is what we do most of our work on. It's impacted the most by the UV radiation coming from the sun. It splits into 2 layers, F1 and F2 during the day and in the summer months. So as we get into winter, we'll see less and less of the 2 separate F layers. At night, the F1 and F2 layer combine into a single layer, and it goes up higher. The F1 layer is best for 10 to 20 megahertz during the summer. The F2 layer persists throughout the night and has the highest ion density of any layer except for any weird E layer phenomena. So again, it's not the density of the atmosphere itself at that point; it's the density of the ionization. The F2 layer varies considerably between day and night and with the seasons. So I kind of found this fascinating. This is where I began to pull up some information. I wanted to show some different charts. And really, you don't need to look at these in detail. This is just trying to give you an idea. So this one was on the October, the last autumnal equinox that we just had. So I grabbed the stuff out of Boulder. A little note, no, not on this one. So you see we've got what it looked like at sunrise. So look at how low the critical frequency is over there. We're talking, like this is like 6 and 1, 2, 3, 4. So we're down here in the less than 4 megahertz is the critical frequency. But as noon approaches, look at how much. Look, that's nice. That's real nice. We got some nice F there. See a little bit of E over here. Then at sunset, this is still hanging around. It's looking good. But then as you see at midnight, when the sun is on the exact opposite side of Boulder, it looks pretty much like that, and things have died off. It depending on the site, the boulder runs every 5 minutes. Pardon?
To one of these,
Oh,
you
yeah.
can definitely hear them because you're sitting there and all of a sudden it just weird chirp comes up
Yep.
and your waterfall has a line of dots coming through it.
Takes about a whole minute to run through. And like I said, it depends. Some of the sites have more frequencies. So it kind of depends. Each one, I mean, this is not a group effort. These are just people that are different science organizations. The military does this a lot. There's a lot of military sites too. So like the University of Lowell in Massachusetts, they have a site. Boulder, I'm not sure exactly who's doing this one, but I'm sure it has something to do with NIST. I mean, you could go out to the websites and do more information and ask what they're up to. So this was on just a couple weeks ago when we moved into fall. So this was the summer solstice. So again, we still see some a little bit of F here, even at sunrise. And look how high that is and how far out that is at noon. At sunset, still very high, but you can see it lowering. And still decent F layers, even at midnight. Because, and remember, this is from Boulder, so it's Northern Hemisphere. So it's all about how much sun you're getting for how long. Because the sun really, it isn't putting out more or less in a regular pattern. It does. That's where the solar cycles come from. But that's not what's doing this. This is basically how long it's exposed to the sun. So this was at the spring equinox. You begin to see that pattern again where you got not quite as good at night, pretty good during the day. And then I grabbed winter. And winter just looks pretty bad. The date doesn't look too bad. Now, this one I have to admit, I cheated on. The date, for some reason, they're having equipment problems on the day I was looking, so I had to adjust to the day before or something like that. But it still gives you the idea of what's going on. So yeah, you can do this type of stuff, compare and contrast with this data. So space weather. This is what the sun is doing to us. The good, solar radiation. It bathes the ionosphere on the day side with UV radiation, along with some charged particles, X-rays, and other hard radiation. Sunspots play a key factor in this. They are cooler, magnetically active regions on the sun's surface. The solar flux is the measure of the 2800 megahertz or 10.7 centimeter RF coming from the sun. It's just a tradition that they look for this one. There is a direct correlation between these two. When the sunspot numbers go up, solar flux goes up. When the solar flux goes down, there's less sunspots. We don't know why, but that's what the science is trying to figure out. The higher solar flux equates to higher critical frequencies, which means higher muffs along the path. So that's what we're looking for. That's why everyone's getting excited with the solar cycle, because we're getting more sunspots, which means more UV radiation, which means better ionization. The bad. High energy particles and hard radiation disrupt the Earth's magnetic field, causing RF disruptions. They also, if you saw, I was talking about the D layer. The D layer begins to build up as it gets more and more of these X-rays hitting it. So one of the ways we measure that is through the K index. It's a quasi-logarithmic integer scale from 0 to 9, quantifying the disturbance of the Earth's horizontal magnetic field. 1 indicates calm, while 5 indicates and higher indicates a geomagnetic storm. So it's basically on the ground, there are these magnetometers that measure the Earth's magnetics, the Earth's magnetic field. And they assign a number to it based on where it's at. Those are updated, depends like every 3 hours. And those also, you begin to hear, if you read some of the reports, they'll talk about upper, middle, and lower latitudes. The A index, or the planetary A index, is a linear scale of the daily average level of the geomagnetic disturbances. So it takes that K, turns it into from a logarithmic to a linear, and takes the average of all the sites over the course of the day. So it is looking in the past. This is an interesting little fact. The label K comes from the German word Kennziffer, meaning characteristic digit. Think of it, this is a note I had for myself. Think of it as similar to a barometric pressure. As it is rising, that means there's a geomagnetic storm coming. As the number goes down, things are starting to calm down. So think of it as your barometer. The K indices, so the A is from the past, an average of the past, and put it together for the day before. The K, though, is within 3 hours. So that's where you're going to get your, if you see that number rising, be on the lookout for a geomagnetic storm. No. So here's the ugliest space weather. So that's normal stuff that happens every day. This is the CMEs, or coronal mass ejections. That's basically where big chunks of the sun's particles come flying out. Hopefully not at the Earth. Solar flares. You learn about those in school. Just basically a lot of energy leaving the sun at a certain point. Those go from class A. I'm not sure exactly what they are. The A, B, C, M, and X. But those are basically, A is the smallest and X is better turn your equipment off. And then those cause geomagnetic storms. G1 class is minor, all the way up to G5 severe. And then, so these things can actually cause major radio disruptions, communication blackouts, GPS disruptions. If you're a runner and you use your GPS, you know when there's something going on, because it's like, why is it taking forever for my GPS to sync up? Some days you'll step outside and it syncs up like that. And sometimes I'm like, it's been 10 minutes. Come on, man. And then I take a look and it's like, oh yeah, we got a G2, G3 storm going on right now. And some of them can even cause EMF damage, like the Carrington event. This happened on September 1st and 2nd of 1859. Scientific historians believe it was a CME, possibly two of them. One came and kind of cleared the path for the other to make it even more impactful. There were basically Morse code readers were bursting into flames. Wires were melting. It was insane. I mean, and these things happen. I mean, we had one in 2001. Nothing as bad as this. This is like one of the worst that happens. I think so, but this is worse than that. This is some nasty stuff. So think about it this way. K5 is the beginnings of the storms. K5 usually means it's a G1, all the way up to K9, which means a G5. So as I mentioned, you have a solar cycle. So first of all, the solar day is 27 days. It takes the sun from one point 27 days for it to rotate back around and see us. We actually have satellites, the stereo system, which actually has satellites looking at the backside of the sun, telling us what's coming up, which is really, really nice. We didn't have those years ago. Now we have that information. And if you take a look, I mentioned Dr. Tamitha Scove. She does a lot of stuff dealing with the stereo images and showing you what's coming up. So we know what's coming. We can see that stuff coming. And it's kind of some fascinating stuff. But here, this is the sunspot cycle. It lasts about 10.7 years, give or take a bit of time. And you can see we started recording this stuff in 1750, and you can see the rhythmic pattern. And each of these numbers on the bottom there represents a solar cycle. So we are in cycle 25 right now. And you can see some are bigger than others. The bigger they are means more UV radiation, which means better critical frequencies, better MUF, but it also means the sun is more active. So we do end up getting more of the nasty stuff as well. But if you take a look, I did not include the chart. There is a lot of stuff talking about how frequently we get that stuff. Even when the sun is its most powerful, it's still not as bad as all that. So as I said before, solar flux has a direct correlation to the sunspot number. So we started measuring solar flux in the early 2000s. And as you can see right now, this is us right now. That's not too shabby. So our solar cycle is 25. It basically started in December of 2019. What happens is they saw sunspots appearing with a different polarization. So each cycle begins with a new set of sunspots at a different polarization. And it always starts off at a minimum. So on the south pole of the sun in December 2019, they began to see opposite polarized sunspots, and that harbored that brought in the next one. So at that point, we had a minimum smooth sunspot count of 1.8. That's the other thing too about sunspots. It's a smooth number. It's not the actual, okay, I'm looking at the sun, I see 3 of them on there. It's a smooth number. It means that they take, average over a period of time. So far, the current max we've had has been 68.9. So we are moving up. It's expected to last till 2030. I keep looking at all the predictions, and they are all over the place. Some people say we're going to be moving into a Maunder minimum where we're getting almost nothing. Some people are saying it's going to be crazy insane, and no one really knows. We really, really don't know. I think it's kind of like the stock market. Past performance does not necessarily guarantee future performance. So you can see it can go all over the place. But here I got a bunch of different resources for the space weather forecasts. WWV and WWVH both transmit at on their respective frequencies. 18 minutes after the hour for WWV and WWVH at 45 minutes past the hour. If you click on that link over there, you can also see the text of the message that they're sending out. W1AW sends out K7RA. Ted Cook does a weekly propagation bulletin. This is what got me into this to begin with. When I was practicing Morse code, they do the propagation bulletin until the weekend when they do the DX bulletin. And I was copying him all the time. I'm like, what do these numbers mean? What is this guy talking about? That's what kind of got me interested into reading this stuff. And he and a bunch of other guys do a lot of talk about what they saw, what they're expecting to come, things of that nature. And it will tell you what the past was, and then they give you the future predictions. NOAA Space Weather Center has a lot of good information on there, as a spaceweather.com. Dr. Tamitha Scove, she talks on Ham Nation. She has her own show. I follow her on Facebook. She puts a lot of really good information out there. Then there's a couple other ones, the real-time band conditions, and then the W5MMW does some interest. So they do a lot of those little drop them in your website type things.
The Channel 5 newscast on weather, but for outer space.
Well, it was also fun because right before COVID, she actually went out and got her ham license, and she's a licensed amateur radio now. So it was kind of fun. She was doing with that. So here is the report from the 1800 UTC report earlier today. So you see it talks about for October 3rd, the solar flux was 155, and estimated planetary A index was 24. The estimated planetary K index. So remember, the K is both high, mid, low, and planetary wide. So they can do all these averages. Was 2. So things are pretty quiet. The space weather for the past 24 hours has been minor. Geomagnetic storms reached the G1 level, so that's really nothing. Radio blackouts reached an R1 level occurred. So the next 24 hours predicted to be moderate. I don't know if this is going to work. I did record these. I don't know. I don't even know if I'm getting it out here. No, it doesn't look like I did. Yeah, it actually is pretty. It is pretty quiet. I did 15 megahertz last night, and I did 20 megahertz tonight. And one of the interesting things is the noise at my QTH is just absolutely horrible. You can hear the sweeping sound coming in. So it was nasty. Some other resources. I got a lot of the stuff out of the ARL handbook. They have a very nice section talking all about it. There's also. They talk about propagation of RF signals, and they talk about the sun, the earth, and the ionosphere. So there's some good websites there. I also borrowed heavily from Propagation Radio Science by Eric Nichols, KL7AJ. His book was not so much about propagation per se. I mean, I know it has it in the title. He talked a lot more about the science behind it. He gets right into why does ionization occur? What does ionization really mean? What is mean density electron field? How do these things get pulled off of there? He goes into some real deep stuff, some equations and things of that nature. So it was a fascinating read with a lot of details. I mean, I started glazing over the E stuff. It was unbelievable. And then there's also the Digison map, which I showed. And then there's also a list of them. And I think the list has actually more of them. So here are my key takeaway points. Higher solar flux means a higher MUF, higher MUF on your path. Higher geomagnetic A and K indices means more noise. And then know which band you're using depending on the time of year and time of day. Certain bands just are going to be closed. One of the things I didn't mention was that happens a lot with 160 meters. You actually get the LUF is higher than the MUF. You get this weird inversion. That just means the band is closed. You cannot, there's just no way you can do it. So you have to go out there and try. Because as you see, these bands are open. You just have to find out, just try to be a little smart which ones you're trying to go to, which ones you're communicating on, and you should have lots of success. Any other questions? All right, thank you.